Okay, let's settle in for part 2 of our sequences and linear modeling. Basically, we're fitting a line to data, and this is our snowman example. So let's go ahead. The last thing we did was we found an equation of the line in point slope form because we have a point, 331, and we have the slope, negative 7.5. From that equation, right? We call that equation point slope form, again, because we have a point, 331, and the slope, which was negative 7.5. Okay, so let's go ahead and keep going. Find the units of measure for the slope, m, also known as rate of change. Oh, look it, I wrote that already. Using the context of the problem, write a short sentence explaining the meaning of the slope in this problem. So when it wants the units of measure, that wants us to say, okay, well, at what rate is he decreasing at, right? So any kind of rate of change is always going to be a change of x over a change of y. So let's go ahead and make a note of that off to the side here. So basically a rate of change right, is basically the change in y over the change in x, right? So you might recall that the slope formula looks like this: y minus y1 over x minus x1. Sometimes you'll see y2 minus y1, x2 minus x1. Lots of different ways to write it with the variables, but essentially what you're saying is how much change in the y values over how much change in the x values, right? So when we're looking at our snowman here, right, what were we comparing? We were looking at time in hours over height in inches, right? But specifically, we're going the change in y values, so the change in height over the change in time. So let's go ahead and write that out, right? What are our units of measure? So this is going to be a change in height, right, over a change in time. Or specifically, height was measured what? Inches. And our change in time, our time was measured in hours. So this is going to be inches per hour, right? We could say inches per hour, right? Using the context of this problem, write a short sentence explaining the meaning of the slope in this problem. Well, okay, so my slope was what? We got negative 7.5. I ran out of space to write an to write a sentence, but we will squeeze that in right here. Let's go ahead and write, right? What are we going to say? If it's negative 7.5 over 1 hour, right? Because the decimal here is going to be my numerator, and my denominator is going to be 1. So what we're going to say is that he's losing negative, right? He's losing 7.5 inches every hour, right? Or he's shrinking by 7.5 inches every hour. Or he is losing 7.5 inches in height every hour. There's lots of ways to describe, but what we need to say is how many inches per how many hours, right? So we're going to say the snowman is shrinking, and shrinking is going to be the negative for us because shrinking means that it's getting smaller, right? So the word shrinking is actually going to be the negative sign. So the snowman is shrinking 7.5 inches every, I'm running out of space, every 1 hour, right? So that's a sentence that would describe what's happening. The snowman is shrinking 7.5 inches every 1 hour. The snowman is losing 7.5 inches every 1 hour, right? The snowman is decreasing 7.5 inches every 1 hour. Whichever word you use to describe the action, that has to be a negative word to denote that he's losing height. All right, moving on. Write the equation of this line in slope-intercept form. So here's a new form, right? Slope-intercept form. This equation gives us a linear model. So this is what linear models look like, right? So this is an equation up here, right? Point-slope form is an equation, but it is not what linear models look like. Linear models are slope-intercept form, so that we have to keep in mind. For the snowman's height based on the time since it was uncovered. Okay, so we're going to basically take our equation that we had and we're going to convert it to slope-intercept form. So let's go ahead and put slope-intercept form. Let's make some notes over here. Am I writing in the right spot? No. So let's go ahead and make some notes here, right? So slope-intercept form is essentially the one that's most often used, right? Y equals mx plus b. Or sometimes y equals a plus bx. They are the same equation. They're just using different letters to denote different stuff. Do I care which one you use? No, because they are the same. One equation puts the slope in the front. One equation puts the slope at the back and doesn't use the m, right? So it just depends, and we'll get more into that as we look at linear equations more, but this should be somewhat familiar to you. So let's go ahead and copy down our equation. So that's the equation we're going to use. So we're going to say y equals negative 7.5 times x minus 3 plus 31. And we want to basically convert this equation to where it's y equals mx plus b. So notice the only thing they want us to do is get rid of these parentheses, right? They want us to distribute here and then combine our numbers together. So that's what we're going to do. It's already y equals, so that part's good, right? So we're going to say y equals, I'm going to distribute. So negative 7.5 times x is going to be negative 7.5x. Negative 7.5 times negative 3. I'm going to multiply this out so I can get it correct. So I'm going to show you there is 22.5. So this is going to become plus 22.5. Why is it plus? Negative times negative becomes a positive, right? So that's just me distributing. And then plus 31 still, I haven't written that. So we're going to say plus 31. And then notice these are both numbers here, so we can just add those. So 22.5 plus 31 is going to be 53.5. So my equation is going to be y equals negative 7.5x plus 53.5. And I'm going to go ahead and box that in pink there so we know that that's my linear model, right? Okay, so now we have a linear model. We can look and determine and make predictions based on the value that we have, right? That's the point of making a model, is now that we can use predictions, because y represents height, x represents time. So you're going to see in these next little part down here, Why do we want linear models? Well, because it makes guessing easier. Okay, so we've got 3 more here. And then we're going to talk about, well, how strong of a model is it? So let's go ahead and keep going. What is the y-intercept of your model? Using the context of the problem, write a short sentence explaining the meaning of the y-intercept in this problem. So what is the y-intercept in this problem? So let's look at this again, right? So we're going to look at this form specifically. And already above, we identified that m is my slope, right? Or my rate of change. That means b, right, is my y-intercept. Okay, that means b, this value here, is where my graph crosses the y-axis. Okay, so let's look to see if that's true. My b is what? If my equation is this, let's go ahead and write it one more time so we can see here, right? So we already identified this is my slope, right? That means this is my y-intercept. Right? This is my rate of change. He's losing 7.5 inches every hour. This is what? What is this 53.5? So let's look at my graph. I'll try to zoom out here a little bit so we can see more. Do I even see 53.5 on the graph? I don't. The most I see is 48, right? But if I were to keep going, right, and I extended my line out, what is that 53.5, right? That would be the point where, the point where my graph is crossing the y-axis, which would mean what? Right? What does this point represent in terms of height? Well, in terms of height, it would be 53.5, right? That's my y-axis. What does this value here mean in terms of time? Well, if it's on the axis here, then that means time is 0. So what is a y-intercept then, right? What is this saying, right? Hopefully you're catching on that a y-intercept is basically the height of my snowman when at time 0, right? When I first took him off the plane, right? So at time 0, this is the height in inches of my snowman, right? So let's write a short sentence in context of this problem. So we would say, the snowman is 53.5 inches tall when first put in the desert. Desert has one S, right? Oops, you can't see. Sorry, I'm zoomed in too much. Desert has one S. Dessert has 2. Do you know how I know the difference? A desert has just sand. That's all a desert is, right? So sand. Dessert has sugar and spice. So it has 2 S's, sugar and spice. Desert just has 1 S. That's how I was learning. That's how I was taught to remember the difference between desert and dessert. Right? So the snowman is 53.5 inches tall when first put in the desert. Okay, so now we've decided our slope, we've got our y-intercept, we have a good model, we know how tall he was at the beginning, we know how fast he's shrinking. Done. Now we can make some predictions. So use your linear model to predict how long it took for the snowman to melt completely. Ooh, so here's the trick, right? How long did it take to melt completely? Well, if he's completely melted, what do we know? Right? If he's completely melted, that means his height is 0, right? He's gone. right? So what is this really asking us to do? Use the model, right? So this equation here, to predict how long is x, isn't it? How long is time, which is our x-axis, right? So how long it took for the snowman to melt completely, where my height is 0. Height is y. So what it's wanting us to do is plug in 0 here, right, and solve the equation. So let me see if I can squeeze that in here, right? So we're going to say 0 equals negative 7.5x, because we don't know. That's what we're looking for. How long? X. We don't know. So that's going to be the variable. Plus 53.5. So we want to solve for x. That means we're going to first subtract 53.5. Right? So I'm going to go this way just so that I have some space to solve out. So now we're going to get negative 53.5 equals negative 7.5x. If I want to solve for x, the next thing I'm going to do is divide by negative 7.5, because negative 7.5 divided by 7.5 is 1, which just leaves x. But whatever I do on one side, we're going to do to the other. And so I'm actually going to divide 53.5 divided by 7.5, right? So we're going to say negative 53.5 divided by 7. Oops, I forgot the negative. Negative 7.5, right? So negative 53.5 divided by negative 7.5, and we get 7.133. So x is going to be 7.1333333. What does that mean? Right? It's one thing to solve my equation, but what does this mean? Right? So now you have to think and take it one step further, because in advanced algebra, we've got to be able to explain everything we're doing. So use the model to predict how long it took for the snowman to melt completely. So how long did it take for him to melt completely? A little over 7 hours, right? So we're going to say that. It took a little over 7 hours for him to melt completely. Okay? We want to describe what's going on, right? All right, and then the last question here says, use your model to estimate. So again, we're estimating, right, or predicting, notice, how tall this time. Tall is what? Tall is height. Height we know is y, right? My height comes back as my y-axis. So estimate how tall the snowman was at 2.5 hours, right? 2.5 hours is time. So we know, in this case, we know x. So we're going to do same thing. We're going to use our model, right? This equation here. And we're going to say, and we're solving for y this time. So we're going to say y equals, he's losing 7.5 inches every hour. Well, if he was out for 2.5 hours, that's what we're looking for, right? Plus he started at 53.5, right? How tall would he be? Well, this is something I can just plug into the calculator. So we're going to do that. So negative 7.5 times 2.5 plus 53.5. Right? So we're gonna, oops, sorry, I can't see it. There you go. So we're gonna multiply and then add 53.5, 34.75. So what does that mean, right? We get y equals 34.75. Again, what does that mean, right? Well, go back. Estimate how tall he was. Oh, so this is how tall he is when? 2.5 hours. So at 2.5 hours, right, the snowman is about 35 inches tall. Right? We don't have to be exact with our values when we're doing real life examples, because no one would say he was about 34.75 tall, right? We'd say, oh, it's about 35 inches, right? So that's what we're looking at. Okay, so that is how we make a model, right? We started off with how do we write a model? How do we get that model from one form to the other? So we did that. And then why do we use a model, right? We use it to make predictions. Okay? So the last thing we're going to talk about, I will actually make a third video for. And that's about how do we know if our model is a good model or not? How do we know if it represents what's happening? So be on the lookout for another video.